Okay, we're now in section 21.4, RLC series circuit, and let's advance the PowerPoint. Now we're ready to consider what happens when a resistor, capacitor, and inductor are combined in an AC circuit, as shown in the top figure. Since this is a series circuit, current is the same at all. Since this is a series circuit, current is the same at all points in the circuit at any instant and varies sinusoidally with time, as shown in the bottom figure. The equation shows this mathematically. I equals I max sine 2 pi f of t, or I equals I max sine omega t. Okay, now that the voltages across each element might or might not be in phase with the now you know that the voltages across each element might or might not be in phase with the current. These graphs will show us the voltage-current relationship for each element. Figure B shows the instantaneous voltage across the resistor. Figure B shows that the instantaneous voltage across the resistor is in phase with the instantaneous current. So what the voltage across the resistor, there's no phase lag. There's no phase lead or lag. It's the same as the source voltage. Figure C shows that the instantaneous voltage across the inductor leads the current by 90 degrees. Figure D shows that the instantaneous voltage across the capacitor lags the current by 90 degrees. The net instantaneous voltage supplied by the AC source equals the sum of the instantaneous voltages across the separate elements. So we have delta V equals delta VR plus delta VC plus delta VL. This doesn't mean that the voltages measured with an AC voltmeter across R, C, and L sum to the measured source voltage. In fact, the measured voltages don't sum to the measured source voltage because the voltages across R, C, and L all have different phases. We can use a technique involving vectors to account for the different phases of the voltage drops. We can represent the voltage across each element with a rotating vector, as in the figure here. The rotating vectors are referred to as phasors, and the diagram is called a phasor diagram. This particular diagram represents this. This particular diagram represents the circuit voltage given by the expression shown here, where delta V max is the maximum voltage, which is the magnitude or length of the rotating vector or phasor, and phi is the angle between the phasor and the positive x-axis when t equals 0. You can think of the phasor as a vector of magnitude delta V max rotating at a constant frequency so that its projection along the y-axis is the instantaneous voltage in the circuit. Because phi is the phase angle between the voltage and current in the circuit, the phasor for the current, which is not shown here, lies along the positive x-axis when t equals 0, and is expressed by this relationship. I equals I max sine 2 pi f of t. Phasor diagrams are useful for analyzing the series RLC circuit. Voltages in phase with the current are represented by vectors along the positive x-axis, and voltages out of phase with the current are phasors in other directions. In the figure on the left, delta VR is horizontal and to the right because it's in phase with the current. And delta VL is represented by a phasor along the positive y-axis because it leads the current by 90 degrees. Delta VC is along the negative y-axis because it lags the current by 90 degrees. Now, let's add the phasors as vectors as shown in the right-hand figure. Okay, I lost my place. From this, we get the equations here. So Vmax is equal to the square root of VR squared plus, in parentheses, delta VL minus delta VC squared. Don't square the individuals first. And the tangent of phi is equal to VL minus delta VL minus delta VC divided by VR. In these equations, all voltages are maximum values. The equations are also valid for RMS values. The equations are also valid. The equations are also valid for RMS voltages. I'm sorry. This figure reminds you that the voltage across the resistor, capacitor, and inductor are not in phase. So you can't simply add them to get the voltage across the combination of elements or to get the source voltage. A nice mnemonic device to help you remember the phase relationships in RLC circuits is Eli the Iceman. E represents the voltage, I the current, L the inductance, and C the capacitance. So the name Eli means that in an inductive circuit, the voltage leads the current. In a capacitive circuit, ice means that the current leads the voltage. Okay. Here are the voltages in terms of Ohm's law. So you can write the equation for delta V max as shown. V max is equal to I max times the square root of R squared plus X sub L minus X sub C squared, quantity squared. So you need to do the X sub L minus X sub C before squaring them. Now, we can define the impedance Z as shown. Z is equal to that square root of R squared plus X sub L minus X sub C squared. And rewrite our voltage equation in the form of Ohm's law. V max equals I max times the impedance, with R replaced by the impedance in ohms. This impedance and the current in an AC circuit depend on the resistance, the inductance, and the capacitance, and the frequency, because the reactances are frequency dependent. We can represent the impedance Z with a vector diagram such as the one shown here. The right side of the triangle is X sub L minus X sub C. Its base is R, and its hypotenuse is Z. If we apply the Pythagorean theorem to this triangle, we get our definition of impedance. Also, we can calculate the phase angle. Tangent theta equals X sub L minus X sub C over R. So really, to calculate the phase angle, you would take the arctangent of X sub L minus X sub C over R to get theta. Okay, now this table provides impedance values and phase angles for some series circuits containing different combinations of circuit elements. And this is a good table to reference. The most important one is the bottom, the square root of R squared plus X sub L minus X sub C squared. Notice that the X sub L always comes first in this equation. And let's get some problem-solving strategies for RLC circuits. Number one, calculate the inductive and capacitive reactances. Number two, use the inductive reactance and the capacitive reactance together with the resistance to calculate the impedance of the circuit. Number three, find the maximum current or maximum voltage drop with the equivalent of Ohm's law. Number four, calculate the voltage drops across the individual elements with the appropriate variations of Ohm's law. And number five, obtain the phase angle. I will do a detailed homework experiment to show you how you go through this process, and probably the book shows you examples too. So this ends the RLC series circuit section. The next section we will discuss is section 21.5, power in an AC circuit.